That, yep. Can everybody hear me? Wave at the back. No, it is on. Any better? I might have to hold this. Okay. Give me a minute while I locate my presentation. Google Drive, go away. Okay, right. So yeah, good morning. I was asked to come and speak about citizen science and exoplanets, and that's what I'm going to do. I'm going to talk a little bit about my experience with two citizen science projects, Backyard Worlds and Planet Hunters NGTS. So the caveat to this is I have to leave right at the end of the session to get back to the UK. So if you want to talk to me about any of this, please message me on Slack or my email's on the slide here. Okay, so I'm going to start with a brief introduction to exoplanets. We've not had a lot of exoplanet chat during this week so far. The first exoplanet was discovered in about 1995, and it's called 51 Peg B. And it was found via radial velocity measurements. So this sort of heralded the era of high precision radial velocity. By this, we're sort of talking meters per second. We now have centimeter-ish per second resolution on some of these instruments. And the infographic at the bottom shows you what we're looking at here. Essentially, we're taking spectra of the star, not of the planet, and we're looking for the movement in the lines of the star as the planet exerts a gravitational pull on the star. And the first planets found this way are sort of defined by what could be detected. So they were quite massive. In the case of 51 Peg B, it's got a mass of half that of Jupiter, and it has an orbit of 4 days. So not like anything we have in our solar system. We now have over 5,500 planets known, and 4,000 of those were discovered via the transit method. And the transit method has a huge benefit over radial velocities in that it's much easier to get data this way. Radial velocities require you to spend time with very few high-resolution spectrographs, getting spectra of stars, and trying to determine an orbital period from the spectra you get. The transit method, however, you just have to take lots of high cadence images of your stars, which tend to be quite bright, looking for the dip as your planet moves in front of the star. The planets are not self-luminous, so they block out the light from the star, and you get this characteristic dip as the planet moves across. Bigger planets make bigger dips, as you might imagine. And from the length of the transit and the depth of the transit, you can determine the radius ratio of the two objects and the brightness ratio of the two objects. So if you have decent stellar parameters to start off with, then you can figure out the size of your planet. And then we would use targeted radial velocities to get the masses. And in some cases, for things in circular orbits, we only need maybe 4 radial velocities now, not 50 over a few nights to do this. And since the transit method sort of became popular, the numbers of exoplanets have completely exploded. So we now have these missions and facilities I've called transit factories. Some of you might recognize them. I'm not going to do a show of hands. We have this little one in the middle. Here is Corot, which was an ESA spacecraft, and it found sort of 33 exoplanets. One in the middle here is WASP, or Super WASP, has found nearly 200 planets. And then the next generation that took over from this, we have Kepler, which with a ridiculous number of planets. TESS is up here at the top right. And NGTS, which I'm going to talk about, is over here at the top left. And then the bottom right is an ESA mission, Plato, which you might not be familiar with, which should launch in a couple of years. And you'll probably notice from the pictures I've put here, the thing that seems to be in common with most of these is that they are multi-camera instruments, either separate cameras or lots of separate detectors to provide a huge field of view to survey thousands, if not millions of stars at once to get your light curves. And Plato will be quite unique in that it has this huge field of view, but it also has overlapping cameras. So it will be able to get higher precision photometry for the middle of the field compared to the edges of the field. NGTS at the top left has separately the cameras move separately, so we can observe 12 different fields at a time. And obviously Kepler and TESS just sort of point as they point. So this type of photometry has revolutionized astrophysics in terms of exoplanets. We're now finding exoplanets, but also other science that requires high cadence light curves. So pulsations, variable stars, all sorts of weird and wonderful variable stars. But obviously we're producing tons of data. So TESS takes light curves I think it takes a data point in high cadence mode, something like every 20 seconds, and it stares at a field for 30 days. So we're producing a lot of data here. So I'm going to talk about NGTS, which you might not be familiar with. It's mainly run out of the UK. We're a consortium of institutes that do include the University Observatory of Geneva, DLR, which is the German space agency, but also the universities of Leicester, Warwick, Cambridge, Belfast, and yeah. So we have 20 centimeter telescopes that are located in this very fancy shed at Cerro Paranal. So at the top of the picture on the left mountain, you can see the VLT telescopes, and on the right mountain, you can see the Vista telescope. We observe in the optical similar to TESS, so it's a wide I band. Our cadence is 13 seconds. We do use a 5-second exposure, and we have similar precision to TESS. And we were designed to look for Neptune-sized planets around cooler stars, because if you're looking at smaller stars, you can find smaller planets. The contrast ratio is better for you. We found 30-odd planets so far. We've contributed to discoveries from 40 others and over 100 publications on various other things: eclipsing binaries, brown dwarfs, flaring objects, cluster science, dippers, because you find tons of stuff in your fields. So I've got the PI's email addresses at the bottom there. So if you are observing relatively bright things, brighter than 15 and a half in the I band, and ground-based photometry is useful for you, then do get in touch. Oh, I think we have 2 data releases that are public and are accessible through the ESO archive if you just want to mine what we have as well. So I'm see if I can get my little video to work. So this is our publicity video, if you like, of how we operate. So the very bright thing is the moon. And I'll come to that later. So we can operate all 12 telescopes separately, or we can use them together to get higher precision photometry on fainter sources. Now, obviously, so we've found a few planets. 2 you may have heard of. I'm just going to highlight, but not for very long. So NGTS 1b was the first thing we found, and it probably got picked up because our early sets of data were not particularly huge. We were still testing out and calibrating, and we found this thing that looked like an eclipsing binary around an M dwarf, and it turns out to be a hot Jupiter, which was actually really exciting for us. Hot Jupiters around low mass stars are really rare. And if you think about how planets form in disks around stars, this is perhaps not a stupid idea. So if you are a more massive star, you have a more massive disk, you can form a more massive planet. If you're an M dwarf, you're not going to be able to have a huge disk, so it's unlikely you're going to form Jupiter mass planets. And there are only about, I think, 7 known at the moment. NGTS 4b is very much at the other end of the scale. It's a 20 Earth mass planet around a K dwarf. It has this incredibly shallow transit, and I think, certainly when we published the paper, this was the most precise ground-based transit that had ever been done. So onto the data. Those planets and others were essentially found by hand. We have not a very big team of people, and we search through our data, eyeballing the light curves essentially. So we run a box least squared algorithm, which is the little green box you can see here on our data. And that means we're already biased to certain types of transits. We can't find very short transits. So things orbiting white dwarfs have transits of 5 minutes. We're not going to pick those up, very deep, very short transits. But things that last a couple of hours and that are at the 1 to 50% level, we're going to detect. So we run our BLS, and then everything gets archived into these pages called OPIS, which looks a bit like this. And then we have teams of people, two per field of stars, who scroll through and look at our light curves. So we look at the light curves. See here, this is NGTS 1b. We're looking to see if things look real. You've got the periodogram next to it. Because we're ground-based, we suffer from a lot of aliasing. So we have aliases with the day-night cycle. Because we observe in the I-band, we sadly also get aliasing related to a 28-day moon cycle. So we have to be pretty careful about what we're picking up here. We get zooms in of the eclipse, so you can see the BLS here in the red panel. It's clearly not got the depth, but it's identified the eclipse, and that's fine. We look at the phase folding, we look at primary eclipse, secondary eclipse, and we look at odd even transits because BLS is quite stupid and it's very good at finding transits, but quite often it will find a transit and no secondary eclipse, if you like. And then when you compare the next transit along, it has a significantly different depth to the first transit that you see. And at that point, you realize that actually your period is twice and you're getting a primary and secondary. I'll show you that a little bit later. Although we also look at the images because we have big pixels, not as big as TAS, but confusion and blending is still an issue for us. So we need to check that we're not blended and looking at background objects or two things that could mimic where variability is going to mimic a transit. Anyway, this is a lot of work. It's a lot of labor to find rare things. And so we moved towards citizen science. And we launched the project in 2021. We had somewhat of a captive audience because at the time, Planet Hunters TESS and Kepler were out of data. So we turned up with a similar workflow and lots of data for people to play with and basically pinched all their citizen scientists for a while. So that worked out quite well for us. And this was made possible because Meg Schwann moved to the UK, to Belfast, to join our consortium, and she'd been involved in Planet Hunters TESS, so she helped us set this up. And when we launched, I gave a talk at the National Space Centre in the UK about citizen science in general, and I asked citizen scientists from the Backyard World, another project I worked on, what they thought about citizen science. And I really like this slide. I think it's really, really instructive about the people who are involved in citizen science. And, the fact they can do science on their own terms, in their own time, when perhaps they were discouraged from taking part at school because they were maybe not deemed academic enough, or academia research was not a stable enough career, it doesn't pay well enough in their country, all these things. And, the joy that comes across in these quotes, I think, is really, really nice about why people choose to take part in these projects. So what do we look like? We have a workflow. I'm not sure if you can read that. I'll read it out. Where we ask our citizens to identify features in the light curve. So you get your light curve and we say, okay, can you click on a button that says, is it U-shaped? Ideally planet. Is it V-shaped? Probably eclipsing binary. Is there no significant dip? I mean, is it just garbage? Do you think this is stellar variability? Which probably means there's a standard baseline, but there's quite a lot of wiggles. Or is there a large data gap? And we get quite a lot of this where we have identified periods, but it's because there are giant chunks of data missing because maybe it was cloudy or it rained. And there's, as with all Zooniverse projects, there's a little tutorial button at the top, which shows you an example of each of these things. And you can be done when you've had a go at this task, or you can click to be done and talk, which takes us to the message board where you can talk to other people about, I kind of think this, but this looks a bit weird. What do you think? And get input from other citizen scientists. So, here's a very good example of bad data and an excellent example of where we're missing a ton of stuff. So, the things that our algorithm finds it difficult to distinguish between things being real or not, obviously our citizen scientists are really good at doing, and this has been invaluable for us. We also have a couple of additional workflows, and I've pinched this from Sean O'Brien's paper, which came out earlier this year. So if you can't see this, go read the paper. But essentially, after we've said, is it U-shaped or is it V-shaped? There are further options, which are, is there a secondary transit? So is it flat, or is there a secondary dip? Or is there an odd even difference? So are we looking at, does transit 1 and transit 2, do they look notably different? And here's an example of that. So if you have transit 1 in the blue, no secondary eclipse, and then when you look at transit 2, which is the pink, you can see it's significantly deeper. So BLS has misidentified the period here. It's twice, and we have an eclipsing binary, not a planet. And the way this works is actually pretty clever. So I talked a little bit about this in one of the breakout sessions, but there's a user weighting scheme that was devised by Chris Lintop for Zooniverse. So if he's on Slack, please pass to him with the questions about this, not me. Where essentially users who are really good at identifying a certain type of feature get upweighted, and we trust their identifications more. So we don't trust their identifications on everything more, but just on that particular thing. And this is really useful. So the assumption is that if everybody agrees, they are correct. And people who disagree with that are maybe less good at identifying that sort of feature. And this is how we determine the reliability of our IDs. So there's some stats here. Essentially, as ever with Zooniverse, we have a few users who identify and classify a huge amount of things. Most people sort of identify a few or don't log in and do this anonymously. They click around, they have fun, and then maybe they go and do something else, or they test out a different project. So yeah, the mean IDs per user is about 268, and our median is about 40. And we checked the existing planets that we left in the data, and we're getting a 74% success rate for the known planets in our data, which is really, really good, actually, that our users are finding the known planets that are there, even if the data is not perfect. So skipping on to some results, what did we find? So we whittled down our 105,000 candidates via the various workflows. So that was what we started off with as U-shaped, and then we've whittled them down to 5 candidates. And that did involve a decent amount of eyeballing, but it's a significantly smaller list than if we hadn't done this in the first place. So they're all hot Jupiters, which is maybe not surprising. They're easier to find in our data. Periods of 2 to 10 days-ish, and a variety of host stars. So we've got an M dwarf, which may be, if confirmed, the lowest mass M dwarf to host a hot Jupiter. We have what we thought was a giant, but then when we got the speckle imaging, which is what you can see at the top here, the image is elongated, showing it's probably a near equal mass binary. And that could be really interesting, but we don't know which of the 2 stars the planet's going around at the moment. We think it's an S-type binary, which means it orbits one of the stars, not both of the stars, but we don't know which one. Again, we have a K dwarf, an M dwarf, and various others. And we're now at the point of getting radial velocity data to confirm the masses of these planets. So hopefully we'll have some more results within a year or so of the first confirmed planets. Right, so in the last couple of minutes of my talk, I'm going to talk about a very different citizen science project. So I got, shall we say, drafted in as part of Backyard Worlds in the middle of the pandemic. And it's possibly, yeah, I think it's possibly one of the things that actually kept me doing research while I was stuck at home, homeschooling 2 small children. Having a weekly meeting with everybody in an evening to chat about fun science things really kept me going through that really difficult time for most of us, I think. And Backyard Worlds has a very different workflow. It has a very simple workflow almost. So we have these flip books of moving images, and we ask our users to identify things that are moving. So we just ask them to click on a thing that's moving. You've got the thing in the bottom right, clearly moving, and the thing that's labeled a dipole is moving less. So this is why it sort of appears half bright, half dark in the images. However, despite perhaps the simplicity, we have a hugely active community, and it's been a real privilege to be part of the project and to watch in the 4 years I've been involved with people who have gone from, I kind of think this thing looks interesting in the flipbook, to I kind of think this thing looks interesting in the flipbook, and then I looked it up in Simbad, which has then become, and then I looked it up in various image catalogs. And then I found an archival spectrum. And actually, now I'd quite like to write a paper on this because it's really exciting. And this evolution of our citizen scientists has been really phenomenal and a great privilege to watch. But this is very different from the way Planet Hunters Test works, where our citizens find they might, highlight interesting things to us and do the workflow, but they're not in a position to sort of run away and get RVs and leave the papers, unlike this. So we have our a selection of papers here, some of which I hope you might have read. No judgment if you haven't. But when I put the stats on, so we've got 34 papers, 23 of which are refereed, and 11 research notes. And we've published over 400 new brown dwarfs as part of this project, which is phenomenal. There are only a few thousand known, so this is really incredible. And I don't like using publication statistics as a measure of success, but I think these publication statistics are very much a measure of this project's success. And we have 2 publications led by PhD students, 9 that have been led by undergrads, and 2 that have been led by high school students, quite often on internships, and 7 led by people who are not trained scientists or not trained astronomers, shall we say. And some of the ones that are highlighted here, so the one at the top, this was recently published by Tom, who is an undergraduate student in the UK. Taryn, I think, is also a student. And yeah, so the way the project operates is extremely different and has been extremely useful in terms of finding those weird things that are not highlighted by usual surveys and searches. Because we have people basically saying, hey, that yellow thing that somebody found the other week, I think I found 3 more when I did this random search. And this is where we are finding the rare gems and the things that don't fit the templates. And it's purely led by the interest of our citizen-led science team, which I think is really, really cool. So I'm going to end there with any questions.